All right, so Physics 30s, I want to tackle radioactivity today. I really encourage you to watch that video on radioactivity, the most radioactive places on Earth. It highlights Marie Curie and just some awesome things about radiation. I want to cover the three types of radiation today and also show you a bit of the math that's very similar to that complexity we were learning before about mass defect. I know it's really it's a tedious concept because of how specific you have to be, but I'm confident you can figure that out. When we're talking about radioactivity, the history of it basically is, and it's even mentioned in a couple of those videos, a Frenchman, Henri Becquerel, if I said his name right, he had some uranium salts and he had them in a jar. He put them in a drawer overnight there were some photographic plates in the drawer. So it was in the drawer in the dark all night. And then the next day, the plates had been exposed as though they'd been exposed to light of some kind. So there was ample evidence that there was something being emitted from the nuclei of these heavy metals. In this case, it was uranium. And so um, basically, by the late 1800s, we discovered three types of radiation. Okay, and they're alpha, beta, and gamma. There's actually two types of beta, but we'll get into that. And alpha is two protons and two neutrons. Beta is either an electron or a positron, and positrons are really cool. Or gamma is just a photon. Okay, so we kind of we'll look through those as we go through as we look at this. This graph is really worth looking at because I remember when I was first learning chemistry, it made sense to me that if you had, like 6 protons, you'd have 6 neutrons. If you had 15 protons, you'd have 15 neutrons. Well, it starts out that way, but what's interesting about elements is that they actually acquire more neutrons than protons in order to stay stable. If that wasn't the case, then as you can see here in this graph, this dotted line here would is the 1-to-1 ratio. Okay, let me just get rid of that. It's the 1-to-1 ratio here. So the atomic number on the bottom here, this is the number of protons, and here's the number of neutrons on the y-axis. And it definitely deviates from the 1-to-1 ratio. And so what it confirms to you is that extra neutrons provide stability. Okay. And that's the case in all of the isotopes that we see, especially say above 20 protons or whatever. Okay, so above calcium or whatever it is. Okay, so you start, and the thing is, what's cool is if you're not on this line. Okay, so this line here is the stability line. Okay, where the ratio of protons to neutrons is kind of played out. They're the most stable. If you're not on that line and you're an element, you will undergo what we call decays. You will release particles or photons, but in this case, this one really shows the particles. You will release charged particles, either electrons, positrons, or alpha particles. You will release those so that you can get on that line, okay, because that's the line of stability. And you'll notice too, again, this confirms it. Look at this. The graph runs out here just past 80, okay, because nothing is inherently stable past lead and bismuth, okay, primarily 83. You get above that, and those elements over time will decay. And the dominant one here is alpha decay. So you see all these red arrows show alpha. So that's that's losing 2 protons and 2 neutrons. And these beta decays show that you're either converting a proton into a neutron or a neutron into a proton, and that'll make sense as we go through that. So a very interesting graph because it shows that stable isotopes have technically higher levels of neutrons. Okay, and yeah, sorry, it says it right there too. Above 83, there's no stable isotopes. That's why the graph runs out at 83. Okay, so these are the three. Well, we're going to look at all three. Heavy nuclei that are above and to the right, they're going to experience alpha decay. Heavy nuclei below and to the right will experience beta positive and beta negative. So all of these types of decay that we're just learning about are they occur because the elements want to become stable. So we're going to look at the first one. I guess we should mention this. All radioactive Ks, they follow the conservation of mass and the conservation of charge. So the total amount of charge before and after has to be the same, and the total amount of, well, really it's mass energy, okay? It's really mass energy equivalent. I guess I could say that here. Because some mass, as we've learned, and I didn't really emphasize this yesterday when we were talking about binding energy for just a single element. Why is the total mass of a complete element, why is that less than the sum of all of its individual parts, right? Remember I was showing you this, the sum of all its individual parts. Why is that the case? Effectively, some of the mass becomes energy, okay? Some of the mass becomes energy. And that only makes sense with Einstein's equation, E equals mc squared. So anyway, sorry, I was starting to write that. So the conservation of mass energy. It's really the conservation of mass energy. So let's just look at alpha decay quick. Alpha particles, 2 protons and 2 neutrons. There it is right there. It really is a helium nucleus, okay? And you'll see in questions where you have to actually use the mass of an alpha particle, we tend to just use the mass of helium or a helium nucleus. And I know there's a little bit of discrepancy here because a full complete helium atom actually has 2 electrons as well, which is a little bit more mass than just the helium nucleus, if you can follow that. But anyway, I apologize for that. There's some really tiny errors that if you're really being nitpicky about detail, then it's like, do we dismiss this or not? Because it starts to become so small that it doesn't matter. But anyway, so yeah, the charge on an alpha particle is 2 plus. The mass of an alpha particle, this is sort of the debate here. How accurate are we going to be? Yeah, it's roughly 4 atomic mass units. If you have to use the mass of an alpha particle in kilograms, use the 6.65. I'm going to use the mass of a helium nucleus in my calculations because it's in atomic mass units. Anyway, so I guess the short of it is, anytime you have a question, just use the numbers that are given to you and try not to, lose some hair over, well, do we count the electrons or not? And anyway, so sorry about that. But oh yeah, there's this term here. This term comes up sometimes, transmute. Transmute means you just change. A transmutation is where you go from one element to the next. Isaac Newton and many others like him were famous in their studies of alchemy, which involved the supposed theory that you could take any element and turn it into another one. So we could turn everything into gold. That was kind of the and you've maybe seen that play out in like the Harry Potter movies or whatever. But alchemy went on that premise, which was flawed in lots of ways, but down at the nuclear level, especially in the hearts of stars, transmutation is definitely possible, where you can new elements can be formed. Anyway, so here is, oh yes, and we'll look at these summaries later. And you've maybe seen this in the video. Alpha particles cannot penetrate very far at all. They can't even go through your skin. If I was shooting a beam of alpha particles at you, chances are it wouldn't even hit you because it would stop in the air for starters. But if it was in a vacuum, it wouldn't even penetrate your skin. Okay, alpha particles are really large compared to electrons and everything else, and yeah, they don't penetrate very far at all. You can stop them with a sheet of paper. So here's an example of alpha decay, which I'm going to break down a bit for you. We're going to start with U-238, uranium 238. That's element number 92. And if we produce an alpha particle, like a lot of times you may be given an equation where you don't know what the daughter element is, okay? So the terminology that we use, U-238 is the parent, okay, if that helps. And then what's produced is an alpha particle. That's the type of radiation. But the new element that's left over is called the daughter element. Okay. Oh, that's kind of ugly there. That's really tiny. Sorry about that. Yes, and sorry to all the men out there. Sorry. In nuclear physics, all we make are girls. Sorry. So we have daughters. what's missing too from this expression, and it's always the case, is there's also energy produced. Okay, so I want you just to keep that in the back of your mind, that when these decays happen, we're releasing energy. Okay, now, you know what? I'm actually going to clear that off so you can see this without. Anyway, so you get the parent to daughter and the type of radiation. Okay, and actually, I'm going to leave that plus energy there. Okay, so crucially, we have two conservation laws that have to be adhered to: the conservation of nucleons and the conservation of charge. Nucleons is just the top number. This is seriously just like, in fact, it's even easier than balancing a chemical reaction, I think, because all you do is you make sure that the total numbers, the total top numbers on the left equal the total top numbers added together on the right. Okay, so 234 plus 4 is 238. Okay, so that's the conservation of nucleons. We did not lose any nucleons to the universe. Okay, that has to be conserved. Now the bottom number is the conservation of charge, which is really the conservation of protons. Okay, because when we say charge in the nucleus, the only thing that has charge is the protons. The neutrons don't contribute to the charge, right? So the bottom numbers have to add up. So the total numbers on the left have to equal the total numbers on the right. And in more complex, we could have another element over here or something. If there were more elements, then the same law still applies. Okay, nothing you couldn't handle. It's just simple arithmetic. Okay, so just keep that in mind when you tackle these. It's not meant to be more complex than that. To determine the energy released during the alpha decay, I want you to see that it's actually fairly straightforward. All you have to do is compare the mass of the parents or the reactants. In this case, that's just going to be U-238. The mass of U-238 will be more than the mass of thorium-234 and the alpha particle combined. Okay, the mass of the products. So this is similar to binding energy, that we're dealing with masses here. And also all you do is you find the mass defect between those two, and then you use Einstein's equation, E equals mc squared, or the shortcut. And I know I made a mistake on that in the other video. I'm really sorry about that when I was showing you the calculation. But yeah, one atomic mass unit of mass is equal to 931.5 mega electron volts, of energy. Okay, so here's how that would play out. And I know there's not a lot of space here, but I'm going to do this for you. I'm just going to kind of squeeze it in right here. So what we do, I'm going to actually do this quick. The change in, if I want to find how much energy is released, I'm going to find the mass defect first. Okay, so I'm going to take the mass of the parents minus the mass of the products. Okay, or it's really the reactants minus the product. So this is a little bit backwards. It's not final minus initial, it's initial minus final, because when you have radioactive decay, the energy that's released is equal to the mass defect in this case. So the parent. Now I'm going to just show you this faster. I know I'm not pulling numbers out of a hat here. I'm going to use these numbers. Okay, so if you look down here, here's uranium-238. Okay, it's the mass of it. Whoa, sorry. It always does that when I do that. Sorry. The mass of it is there. It is 238. 238.050788. Okay, that's the mass of uranium-238. And I made thorium-234. Sorry, that keeps jumping on me. Thorium-234 was one of my products. So that guy was 234.043601 atomic mass units. And I also made an alpha particle. Now, I'm going to use here the nucleus, the helium-4, the mass of helium-4, okay? I know I mentioned earlier that this would also include the electrons, but we're going to basically assume that's negligible for this point. And again, you should use whatever numbers you are given, okay? All right, so let's get rid of this, and I'll show you what I just wrote. So Oh, well, let me move that up here a bit too so you can see it. So there it is. Okay, so there's the parent, and this is all atomic mass units. Okay, I know these numbers are tedious, but just you have to be slow and punch them in. That means, and I'll just do this work here if you trust me on this. Hopefully you trust me. Okay, so the mass defect then is going to be when I subtract the sum of the products, and I'm going to get, let's see, 4.584 times 10 to the negative 3 atomic mass units. Okay, so that's a really, really small mass defect. But in order to, that's mass, and for me to get that into energy, I'm going to convert it using the conversion 931.5 MeV per atomic mass unit. Okay, so atomic mass units cancel, and I'm left with 4.27 MeV. Okay, now sometimes they want you to do 4 significant digits. I just went 3 here. Okay, but the point is, I just want you to see you could calculate the amount of energy released. Okay, because it's just the difference between the mass of the parent and the mass of the products, and then you convert that into energy. Okay, so that's alpha decay. I think you can handle that arithmetic no problem, and you'll get some practice doing that in the review questions. I mean, at least if you can recognize that, hey, that's an alpha, this is an alpha decay. This is alpha radiation, okay, because you're making a 4-2 helium nucleus, all right? Now, beta decay. This occurs when what's called a beta particle is emitted from the nucleus. Now, there's 2 types. There's a beta particle, beta negative, which is all that is it's just an electron. Okay, a beta negative particle is an electron. Oops. Now, I'll show you how those come about. But here's the fun one. If you get an electron, okay, and imagine if you could get an electron and then all you did was change its charge. So it's now positive. Okay, so it's identical in every way. It has the same mass as an electron, but it's positively charged. That is called a positron. Okay, and it actually opens a whole new world of something called antimatter, which we're going to talk about later. Now, some of you have probably heard about that already. Antimatter is identical to matter in every way, except it has the opposite charge. Or if it's a neutral particle, it has something called spin. It's an opposite spin. It's just like spinning in the opposite direction, if you will. I'll just leave that for now because it gets a little complex. But anyway, so beta positive particles are positrons and beta negative particles are electrons. Okay. So let's look at the beta negative first. Okay. So this is what's really cool inside the nucleus. And here, maybe I'll draw it. I'll sketch it a bit for you too. But a neutron can actually undergo a change and become a proton in its effort to become stable. It's just really cool. So this is the equation here. It shows a neutron becomes a proton plus an electron plus something else. And this guy right here is called an antineutrino. An antineutrino. There it is right there. Okay. Antineutrino. The symbol for that is a V with a bar over it. And you'll see the conventions shortly. If you have a neutral particle and it's an antiparticle, you have to show that it's opposite. And one of the conventions for that is a bar above the symbol. Okay. So what you can see here first is that everything is conserved. Okay, so the top numbers all add up to 1, and the bottom numbers all add up to 0. Okay, so if we start with 1, then we have to end with 1. And if we start with a 0, you have to end with a 0, which you do. Okay, now it's getting messy here. I'm going to back up. Okay, so the conservation of nucleons, here, let's just get rid of that too. Okay, and conservation of protons, both of those happen. Okay, now, what if it helps you? I like visualizing it like this. Here, let's just move this over here so you can just see this. I like imagining a neutron, okay, like this. And the neutron can become a proton. Okay, but and a proton is slightly less mass than a neutron. Okay, and we already know that if you look at the charts. But we also make an electron, a little tiny electron. Okay, so um, the charge is conserved, right? So we end up with a neutral total charge, but there's also a neutrino that's produced, and an antineutrino, and antineutrinos are insanely small. Like you think electrons are small. Well, actually, neutrinos are in the same category. They're really, really small, like 10 to the -31, -32. I'm not sure exactly their mass. It's just it's not zero, but it's super, super small. So most of the time we just ignore the neutrinos or the antineutrinos. Okay, so that is a beta negative decay. Now, I've also seen it written like this, and sometimes here I'll put it right here. Usually we put it, you'll put it as a 0, -1 beta, like this. Okay, they'll use the Greek letter beta instead of E for electron. Okay, so be prepared for that. You might see both, but it's very easy to identify a beta negative decay. And so what we'll say is, okay, let's take thorium-234. We actually got this from the alpha decay. Okay, so this is thorium-234. Let's say it's not super stable and it undergoes beta negative decay. If that happens, we draw an arrow just like in chemistry. So the arrow shows a decay. What one of the products is a beta negative. Okay, and then you can work backwards using arithmetic, and you can say, well, the nucleon number should stay the same, and it does, but the proton number has to add to a -1 to get 90. Okay, so what happens is we change the element, and it's Pa. I'm pretty sure that's protactinium. I gotta look at that one. I always think of a protractor when I think of Pa. But anyway, so that's our products. These are our products. Okay. Now, as a or just to show you I have some space down here. I want to show you how we would do an energy calculation with this one. Okay, so let's just clear that off. What you have to note again, of course, is that this would also produce energy. Okay, I'm going to say that for every single one of these. And if you needed to find the energy released in a beta negative decay, what you would note here, it's not too bad because it's the same thing that we did up here. Okay, we still have to find the mass of the parent and minus the mass of the products. Okay, so the parent in this case is thorium-234, and the product, actually, and let me make a little note here. Thorium would include, thorium-234 as a neutral particle would also have 90 electrons. Okay, it's got 90 protons, 90 electrons, and whatever, a pile of neutrons, whatever the difference is there. Okay, if in the nucleus this is happening, okay, if inside the nucleus, like one of those neutrons inside thorium-234 decides to become a proton, well, it'll do that, but then it'll kick out a beta negative, it'll kick out an electron. An electron will leave the nucleus, okay? But in terms of the conservation of mass, okay, if it helps you, what would have happened here is you still would have an intact, you still would have the 90 electrons, okay, inside the whole atom, okay? So like I didn't change the number of electrons. So what you would have though is technically you'd have protactinium plus, because you'd have 91 protons and only 90 electrons, which you don't have the mass of protactinium positive. You don't have the mass of the ion. But you did create an extra electron, okay? So that would mean you have a total of 91 electrons. Oh, that's nice, because 91 electrons is what the regular protactinium has. Like protactinium neutral has 91 electrons. So what I'm really trying to say here is if you ever have to do the mass, you ever have to find the energy difference for a beta negative decay, the mass of the parent is just going to be thorium-234, and the mass of the products, okay, including the beta negative particle, including the electron, that mass will equal just the mass of regular protactinium, okay? And that would be found like right here, like here she is, where's protactinium? Oh, it's right there. Yeah. So we would just use that mass, okay, the protactinium mass. So we have thorium-234 and then protactinium-234. And we just get the difference between those, and that you can see it's going to be really small here. It's like 601 minus 308 right there. And that little tiny amount of mass difference, you would multiply that by 931.5, just like we did up here. Okay, once you find that mass defect, then you could get the amount of energy released. Okay, so I'm not going to do that one, but I just want you to see that you could very easily. Okay, now the second one is beta positive. These are positrons. Okay, and we're going to look at them a bit later because they do some cool things. But a positron is made when a proton decides to become a neutron. Okay, so here it is right here. The proton, it decides to become a neutron, but in the process, it will kick out a positron. So it kicks out an electron, which is positively charged. And as you can see, the nucleon numbers are conserved. I have to have 1 here, and I do. I have 1 total. And then for the proton number is 1, and I still have a +1 at the bottom. Okay, so that has to be conserved. And really, this is just the reverse of what I showed you already. I showed you this up here. This is a beta negative decay. A beta positive decay, if you want, that would be taking a proton and it becomes a neutron. Okay, but it also makes a little tiny positron and it makes a neutrino this time. Okay, so it doesn't make an antineutrino, it makes a neutrino. I don't know. I always remember, the anti sounds negative to me, so I remember that electrons make, if you make beta negative, you also make an antineutrino, but beta positive makes a neutrino. Okay, and you do need to know that in terms of the products. So here it does show it here, a neutrino. It shows just a V right there. I know it's written kind of funky in the whatever format that is, but typically we just write it as a V. Okay, and in you would do the you would do a mass calculation, mass of the parents minus mass of the products, in the same fashion, although I don't think you'll ever have to do one for a beta positive decay. All right, I guess I could show you a beta positive decay at least. So this would be, here's an example of one. You can start with nitrogen 13. Okay, whoops, that doesn't equal that. Nitrogen 13 can undergo a beta positive decay, and if that's the case, what I like to do is leave a big blank space and then go, okay, fine, you're telling me it's going to undergo beta positive decay. Well, that should be 0, 1 beta, okay, plus, oh, I'm out of space here, plus a neutrino. Okay, so you have to remember that if it's beta positive. But anyway, so then you look at the numbers. Well, something plus 1 has to equal 7. So the only thing that will work is a 6. And then you look at the top numbers. Well, 13 plus 0, or no, if I have a 0 here, then I still need a 13. So then you've identified the nucleon number and the proton number for your daughter element. And I mean, if you don't remember, you can look it up on the periodic table, but 6 is carbon. So we just made carbon 13. Okay, if nitrogen 13 undergoes beta positive decay, you make carbon 13. Okay, so that is beta positive. So anyway, those two are the second forms of energy, or sorry, the second forms of radiation. Beta positive decay or beta negative, it can penetrate a lot deep. It can penetrate a little bit deeper, and you'll see that here. It can be stopped by 3 millimeters of aluminum. but it'll definitely go into your skin. There are much smaller particles, of course, and we'll look at that at the end when we summarize everything. So the last one is gamma decay. This one's really easy. Gamma is the release of a photon. And we typically show it like this, and I'll write another one like it, but you typically just use an asterisk or a star. And that asterisk indicates that element or that isotope has extra energy, that it's excited, it's in an excited state or whatever. And so when it will release a gamma photon, and there's the Greek letter gamma, which would show that there's been a radiation, a gamma radiation. Okay, so yeah, the one example, actually I did have one written here. Where did I put it? Oh, sure. Okay, so yeah, apparently when boron decays, it actually decays to a an excited carbon 12 atom. Okay, and just for a split second, the carbon 12 atom has lots of energy, so it's not stable, so it releases a photon, a gamma photon. Okay, and boom, there it would be. Okay, something like that. Sorry, my gammas are really ugly on this. So, but the point is, if you see an asterisk, they again look like the nucleon numbers and the proton numbers are the same on both sides. Everything's balanced. So we didn't violate any conservation laws, but we definitely made a photon. Okay, and so that photon will leave with the energy that was released. Okay. That also happens, it's worth noting, we're going to talk about it later, but it happens when a particle meets an antiparticle. Okay, so when matter meets antimatter. Okay, and the really cool one, which you should know well enough, we'll look at this later, but that's if you get an electron to meet up with a positron. Okay, they are antiparticles. Okay, well, sorry, they're the electron is regular matter and the positron is antimatter. And what's really neat is if matter meets antimatter, and if they touch, then 100% of their mass becomes energy, and it's the most potent energy release of anything possible in the universe. Like it's many hundreds of times, thousands of times more potent than a nuclear explosion and a matter-antimatter exchange, because it's 100% of the mass becomes energy. It's insane. But here it is right here. We have a negative, or sorry, a beta negative particle or an electron meeting a positron. If those two meet, they produce two gamma photons. So we have mass becoming energy here. Okay, 100% of the mass became energy. So, and that produces gamma photon. Okay, so let's just review kind of the general principles now, and you need to be comfortable with these in any form of theory question. If we were to fire these radioactive particles through a magnetic field, they would interact with a magnetic field, like so. Beta, in this case, we have, oh, let's see. Yeah, these, I'm checking it with my third hand rule. We've got a magnetic field here, a magnetic field that's out of the page. Okay, so the magnetic field's coming out of the page. Ernest Rutherford would have used a very similar setup here. This radiation source is embedded in a block of lead that's got a little hole drilled in it. And so all the radiation will only come out of the hole. It will be absorbed by the lead in all directions. It'll try to, it'll just be absorbed by the lead, but to the right here, it will escape. When it enters the magnetic field, you have to apply the third hand rule. Okay, so this is where you need to remember that we talked about magnets or magnetism. Okay, so the question would be for this particle right here, that beta particle, is that a beta positive particle or beta negative? So to confirm that, well, if the magnetic field is out of the page, you'd use your fingers. Your fingers would have to point out of the page, and your thumb would have to point in the initial direction that the charge was moving. My palm, if I use my left hand, wants to push up. And if I did it with my right hand would want to push down. So this is a beta negative particle. It's an electron. okay? And it's being pushed in the direction that a negatively charged particle would move if it was fired into this magnetic field. What's really important to note is that gamma particles, gamma photons, okay, do not have a charge. So they are undeflected, okay, in a magnetic field. They don't do anything. In fact, you can't even really see evidence that they're there in most cases because they don't do anything in a magnetic field. The alpha particle is positive, and look at that. Using your right hand, because it's a positively charged particle, your thumb points in the direction that the alpha particle is moving, and your fingers point out of the page, your palm pushes down, okay? So this is, this would be the direction that an alpha particle would move. Now, what I'm hoping you'll see here, and it'll make sense when we start analyzing how we detect particles, is if we fired a positron into this, the positron, what you should probably catch right off is that the positron should go in the opposite direction of the electron, and it will. In fact, it will do something like this. Okay, so it would come in and go something like that. Okay, and this would be a beta positive particle. I guess we could write it like that, or E plus, whatever. Okay. But as you remember, hopefully, from remembering charged particles and magnetic fields, the heavier the particle is, see, they're going to experience the same force. So heavy particles won't be bent as far, they won't be bent as sharp of a curvature as the lighter ones. And that's why this alpha particle is just it's sort of sluggish, being pushed away, because it's got way more mass than the positron. But the positron and the electron should have essentially, at least, unless they're bumping into things, they should have the same curvature, but in the opposite direction, okay? Because they have the same mass. So, in conclusion then, I should mention this too. You know how I showed you this chart at the very beginning, sorry, let me back up here. This chart here shows, all of the possible decays as things are trying to become stable. Another way to show that is to show it as a series, okay? And let's face it, most isotopes undergo a series of changes until it reaches a stable nucleus. Excuse me. So look at this. We're going to start here with U-238, okay? It's element number 92, uranium, and it has 238 nucleons. So it's going to start right there, okay? Now, the first most of the time, alpha decay is the quickest way to become stable. Like doing a bunch of beta decays will take a long time. Alpha decay gets rid of 2 protons and 2 neutrons. So when uranium undergoes an alpha decay, it will do this. And now it's thorium 234. But that isn't stable either, so that will undergo beta negative decay. In fact, it'll undergo 2 of those. Click, click. Now it's uranium again, but it's uranium 234, okay, because it lost the alpha particles. But then it loses another alpha particle and it becomes thorium again, but now it's thorium 230. Another alpha particle, it becomes radium 226, and then that becomes radon 222, and on and on. And you can see, though, once you get here, there's some branching going on. The element could decay one more like this, or it could do beta negative, and then decay, beta negative, alpha, whatever. And look, here, we're getting down to what are the stable particles. Look, we got mercury, lead, bismuth, okay? These are the upper limits of stable elements. And anything above that, all of these other elements up here will inherently want to, they'll undergo decays, whatever, and they will want to become like lead, bismuth, okay? So I like that chart because it shows, they call it a decay series because, let's face it, just one decay usually isn't enough for these large elements to become stable. They'll undergo a whole bunch, as many as they need to until they become stable. And then let's just end on this. This chart kind of compresses what we already learned, but you should know alpha, beta, and gamma and their rough penetration, okay? Typical penetration. I guess what we could just compress here, I was going to add one more thing to this. Alpha particles, they could penetrate thin metal foil. really thin, okay? But because they can't even penetrate your skin, okay? But beta particles, so that's electrons and positrons, like you saw in the other one, it's about 3 millimeters of aluminum. Okay, I said that in the other one. Okay, so it can penetrate a little bit further, but gamma are photons, remember, and they can travel through several centimeters of lead. And if you saw that video with that Australian professor, he had a big chunk of lead, and there were some gamma particles that were getting through it. Okay, so inherently, gamma radiation is quite dangerous because of how much it can penetrate. I mean, you can have thick enough walls that you can block it, but gamma radiation can be very disruptive to your cells, to your tissues, and that's what makes nuclear weapons so deadly, is the amount of radiation that they release and the damage that does. So anyway, that's kind of highlighted in the video. So that's as far as I want to go with radiation. I did post some practice questions, and I will also post the answers to those. There was just one kind of, I think it was a beta negative decay, where it wanted you to calculate the amount of energy released. And then the others, you just had to identify what kind of radiation it was. Was it alpha, beta, or gamma? Okay. And so I think you can get those pretty easy. So that concludes radiation.